Hello friends, welcome to C Field Academy. So this is another video on this series of sorting videos we are doing, and today's topic is heap sort. So I am Suraj and let's get started. So these are the four items which we are going to cover today as part of the heap sort. So heap sort is probably one of the complex sorting algorithms, and hence this is the last video of the series of videos. So we will cover with an introduction of the sorting problem, what the sorting problem is, and then we will slowly start with a basic idea behind the heap sort, how the heap sort actually works, the intuitive strategy behind it. Then we will go and see a little bit about what a binary heap is, what a max heap is, and also we will see quickly how to insert and extract operations work in a binary heap. Now the insert and extract operations, and in fact binary heap itself is a complex subject, and hence I have created another video which I'll link in the description. So that video will be a prerequisite for understanding how the heap sort works, hence I recommend you guys to look at that video. I'll make sure to link that video here as well as in the description, so that it makes your life easier, because we will not cover the insert and extract operations in detail. So the video actually assumes that you know the insert and extract operations, how it works. Next we will go ahead and see the algorithm pseudocode, which means the steps in detail, and then we will try out the algorithm on a very detailed example in a very step-by-step. So we'll take an array and then try to sort it using the heap sort algorithm. Then we'll move on to do performance, which is the time complexity analysis, which we do for every sorting algorithm. And finally, before we end, we will actually have an exercise for you guys to basically sort an array using the heap sort algorithm. Okay, cool. So let's get started with the introduction. So first of all, what is the sorting problem? What does it involve? So I think you guys would be already familiar with the sorting problem. It's in fact one of the basic problems that we have in computer science in undergraduate level. So it's nothing but sorting or basically ordering a bunch of numbers in ascending order. Now it's also possible to have lexicographic sorting, wherein like we sort words in a dictionary, but for this video and for the heap sort, we will just restrict our sorting problem to, let's say we have a bunch of n numbers a1 to an which are in some order, and then our output or the sorting algorithm output is basically the same numbers in sorted order, which means an ordering a1 dash a2 dash dot dot an dash in such a way that a1 dash is less than a2 dash, which is less than a3 dash, so on till an minus 1 is less than an dash. So basically sorting those numbers in ascending order. So this is how it looks like. Let's say we have an input unsorted data where the numbers are jumbled in some random order, and we will apply our sorting algorithm, in this case heap sort algorithm, and then we will output the sorted data, which means the numbers in sorted order. So that is the expectations of the sorting problem. Alright, now a little bit about what heap sort is and what properties of the heap sort is. So heap sort is basically a sorting algorithm that uses a special data structure, which is a heap. So heap is a special data structure which is a complete binary tree. So the basic idea or strategy it uses is, it's kind of a improved selection sort, but instead of selection sort where the data was in the array, what it does is it inserts all the items into a tree or a heap, and then once it has inserted and ordered the elements in the heap using some strategy, then we pick the elements one by one from the heap, and when we pick the elements one by one from the heap, we actually get those elements in a ordered list. So that's the whole idea. So, and that's why it's called as improved selection sort, because in a way we select an item repeatedly from the heap. So it is an in-place sorting algorithm, which means it can actually sort the whole data in the whole array, given array. It doesn't need any additional space, but it is not stable. And when we say stable, we are saying if there are two elements with the same keys and they are in a certain order in the input data, the same order is not preserved in the output data. And it is also not online, which means it doesn't work on streaming data. Now, to get a little bit or more understanding on these properties and how they look like with other sorting algorithms, I would recommend you to look at my introduction to sorting algorithms video, which I'll definitely link it here. It's even the first video of the playlist this video is in, and there you can see and compare the different sorting algorithms and the basic strategies that they use. Now, Heap Sort uses the third strategy of that, in which we actually use a special data structure called as a heap. Okay, cool. So so here is a basic idea again. So the whole idea is, first of all, we have the elements in an array like this, and what we need to do is we just organize those elements in such a way that we are forming a heap, which means a complete binary tree. Once we do that, we extract the root element. So the root element of the tree is extracted first, which is this one, and then that element is actually placed at the end of the array. Why? Because it's the maximum element. Now, if the heap is a max heap, then this element is a maximum element, and then we place at the end of the array. And then we now reorganize the data in the heap, which means the heap is again reorganized, and then there will be another element at the top. So we again extract that element and place it at the end of the array, and we keep doing that till our heap is actually empty. So we repeatedly extract the maximum element and then put it in our array one by one. So the first element will go to the end, the next element after reordering will go to the second last, and this is how we keep doing it till our heap becomes empty, and then we are done with the entire list. So before we start with the algorithm pseudocode and how the algorithm, let's just cover a little bit about what binary heap is. Now, I have a separate video for this too, where we discuss all the properties in detail, and I highly recommend you to look that video as a prerequisite for the heap sort algorithm. So here we'll just cover the overview, in a very quick time. So first of all, what is a binary heap? So a binary heap data structure, it's actually a binary tree, nothing but a binary tree, but it has the following two properties. First of all, it's the complete binary tree. It's a complete binary tree, which means all the levels are filled except the last level. Only the last level can remain incomplete, and even in the last level, nodes are filled from left to right. So we cannot randomly have children in the last level. Even if there are children in the last level, then all and those children should start from the left to the right. So that's the definition of the complete binary tree. Then when we say, now heap has a property called as a max-heap or a min-heap, here we will only discuss max-heap. So max-heap has this property that every node, now in the binary tree there are nodes, and every node is greater than or equal to its children. Now if it's a min-heap, every node is less than equal to its children, but here we are only considering max-heap. So every node, now for every node, it has to be greater than its children. So these are the two properties in a heap. Let's see an example quickly. So here is a max-heap, and if you notice, every node, let's say take 44 is greater than its children is 42 and 35. Similarly, if you take any other node, let's say 33 is greater than its children, which is 10 and 26. And let's take 31 is also greater than its children, 14. It only has one child, but even if it has one child, it is greater than that. And also notice the property of the max heap. Now in every level is complete, level 1, level 2, level 3, and the last level is incomplete, and even in this level nodes are filled from left to right. So which means I mean there is basically there is no node. So let's say if there was a child here, then it wouldn't have been a max heap. Why? Because the right child of 31 is still not filled. So that's what a binary heap or max heap is. Now another important property of the max heap that helps us actually sort the input data without needing any additional data or additional spaces. The binary heap can be easily stored in an array using a simple calculation or using a simple formula. So how? So first store the root of the binary tree or root of the heap at the first location, A1, then store its left child at A2 and right child at A3. So in general, if we take any node AI, how we can actually store, or how we can get a parent or a child of the node. The parent is located at I by 2 using integer division, which means the decimal points are ignored. So if it's 3 by 2 is 1. Left child is located at 2 times itself, 2 times I, and right child is located at 2i plus 1. So here is an example. Now this was the heap which we had, and we have 44 as the root. You can see 44 is stored at the first location, and then its left child is 2 times, now 44 is 1, left child is located at 2 times 1, which is 2, and right child is located at 2 times 1 plus 1, which is 2 plus 1, which is 3. So you can see 42 here and 35 here. Similarly, if we take another node, let's take 33. So 33 is the fourth node, and the parent of 33 is 42. So 33 is at 4, and its parent is located by I by 2, which means 4 by 2 is 2. So if we take the node which is 33, its parent is located here, and its children is located at 8 and 8 plus 1, which is 9, which is 10 and 26. So the same pattern. So using this pattern we can store a binary tree or a heap in an array. Alright, cool. Now let's quickly revise how an insert works in max heap. So in fact max heap uses a procedure called as a bubble up. So basically what it does, so basically how we insert in a max heap is, so we first of all just find the let's say here is the heap, existing heap, and we want to insert a new element. So what we do is we find the first available space in the heap, which means the first available space in the last node, and then just insert the node there. So in this case, let's say we want to insert 43, we insert 43 at the first location that is available at the last level, which is here. And then what we do is we call the bubble up algorithm. So that is what the bubble up is, which means we will bubble up this new item into the heap, which means we will try to bubble this item 43. Now once we insert the item 43, the heap property is violated, and hence we need to restore it. How? By comparing it recursively with its parent and then placing it in its place. So that's this algorithm here. If you want to go in detail with an example, please refer to the other video that I have, which will be referred here. So in short, what happens is when we insert the node 43, what we do is we swap up till the heap property is restored. So first we'll swap 43 with 31, and if we swap, then what we do is we check with its parent again, and we keep doing it till we restore the heap property, which means till we see that the elements, which means till its parents are smaller than itself. So once we restore it, we say that we are done the insertion. So insertion involves adding an element at the end and then doing bubble up. Alright, the next important operation is extract root, which is basically removing the root element from the array. Now this is a long algorithm, but it's pretty easy to understand. And in short, what we do is, let's say here is the heap which we have, which is the original heap, and we want to, let's say, extract root. Now extract root means remove the root element. Now here the root element is 44. So simple step is, first of all, what we do is we replace it with the last item in the last level. So in this case 14 is the last element, so we just remove 44 and then we will replace 44 with 14. And once we do, what is the next step? We call the bubble down algorithm. So bubble down means now the new element which we inserted, that is out of place. Now that would violate the heap property, so we need to constantly compare it with its children and then bubble down the element, now in this case element 14, so that it now goes and goes and fits into its position, and then the heap property is restored. Now in this case, let's say we might have to compare with 42, 33 and then 26, because notice 14 is the smallest element, and that's why it will bubble down to the end of the till the leaf of the leaf of the binary tree. Alright, cool. So this was the bubble up and bubble down, which are used for insert and extract root. So now let's come back and see the heap sort algorithm, which we will discuss, and we will see the steps of the algorithm. So heap sort. So we are given an array, and what we need to do, we need to organize the elements into a max heap. So which means first we will organize the given array into the max heap, and then repeatedly retrieve the root element from the heap. And we will use the two calls which we saw, which means the bubble up and the bubble down procedures. So here is the first step. Now the first step, where we need to insert the element into the root, what we do is we start in a loop which is for I equals to 2 to length a, which means here is the given array. So for every element in the array, what we do is we just add it to the heap, which means we just call bubble up ai for every element in the array. So what happens is this array is now organized as a heap. Now when we say as a heap, we still store it in the same array, but it will now be organized in a way that that it now becomes a heap. Once we have done that, the next step is to recursively remove the root element. So that's the algorithm. So which means what we do is we take a variable j, and we start from the length a, which means to the maximum level, and we go till the last element. And what we will do is we will first swap the root. Now aj will be the root of the remaining heap every time, and we will swap it with a1, which is the first element. And once we swap it, which means what we do is we have now placed the root element at the end of the array or the remaining heap. Then the element that we replaced, which is a1, so the last element which we replaced, we now have to bubble down and put it in its place. So we'll call the procedure bubble down. And once we are done, we decrement j and then call bubble down again till we are done, or till we are left with no elements in the heap. So this is the overall algorithm. We will see it in very great detail when we see it with an example, because then it will make much more sense. So here is what pictorially looks like. First we will organize and bubble up, then we will repeatedly replace the maximum element with to the end, and then we will repeatedly call the bubble down algorithm, and finally that results in the sorted array. Alright, okay, cool. So let's now see this bubble down, bubble up and the sorting of heap using a concrete example. We'll take the similar example which we have been taking for the other sorting algorithms. So let's say we have this array, we have 9 elements, and the elements are out of order. You can see 9, 2, 7, 4, 6, 11, 3, 5, 10. And let's apply heap sort on this algorithm. So here is the heap sort algorithm, and as we can see, step 1 and step 2. Step 1 starts with I equals to 2 2 length a, so which means the first I points to 2, so I now points to the second element, which is 2. So this is the value of 2, and then we will call bubble up ai, so which means we will insert the element 2 into the existing heap, which is nothing but only element 9. So let's now do that. So this is what the initial state is. Now initially the heap contained only one element, because for single element we know it is already a heap. And then our bubble up algorithm, if you remember, it starts with inserting the element first to the first available space in the heap at the last level. So what we do is we take element 2 and we will insert it at the first available space. The first available space is the left child of 9, which is 2 here. So we insert it, and then what we do is we do bubble up, which means we will compare the element with its parents recursively till the element falls in its place. So what we do is, first step is to compare 2 with 9. Notice 2 is less than 9, which is okay, because this is a max heap, and in a max heap the maximum element should be the root. So which means there is no need to swap, and 2 has already been in its position, so there is nothing to do. In fact, this is so which means we have inserted element 2 into the existing heap. Cool, no swap is needed, and then we are done. So now 2, nothing has been done. 2 is in its position in the array. That's how this looks like. Now next is I will increment. Now we'll go to step 1 again, and I will increment to 3, which means we have the element 7 and we need to insert the element 7 to the heap. So as we have in bubble up, first step is to insert the element at the end, which means we'll insert it at the last location available. In this case it will be the right child of 9, so 7 will come as a right child of 9. Then the bubble up process will start. So in the bubble up process we compare the node with its parent. So in this case 7 will be compared with 9, and we'll see 7 is less than 9, so there is no need to actually do a swap. The heap property is still satisfied, and we will be done here as well. So I equals to 3 is done. Now similarly we will go to I equals to 4. I equals to 4 is 4, and we have now this 3 elements in the heap. So 4 will be inserted as the left child of 2, because that is the first space available in the third level. So 4 becomes left child of 2, and now what we need to do is we need to bubble up 4. So when we say bubble up 4, what we do is we have to compare 4 with 2, and here we notice that 4 is greater than 2, so which means this is violating the heap property. It's a max heap, and 4 should be actually the parent of 2, because 4 is greater than 2, and hence we will swap. So once we swap, notice what will happen is even in the array also 4 and 2 will be swapped, so which means we'll have 4 and 2 here. So that is the first step, but we are still not done yet. Why? Because we need to bubble up as much as possible. So the next step is to compare 4 again with its parent. Now in this case it's 9. Now 4 is less than 9, so here there will be no swap, because you know the heap property is satisfied. 9 is the parent and 9 is greater than 4. So no swap, and finally we are done, because once we see that there is no swap, there is no need to bubble up further. So we will have this array as final output, final, and then now I will increment again. So I will now become 5, which is element 6. Now element 6 will be inserted to the heap. Now what will happen is it will go to the fifth, which means it will become as a right child of 4. Now as we already discussed, it will take its first available space. So 6 is inserted here, but now we need to also bubble up to make sure the heap property is satisfied. So we'll compare 6 with 4 first, and 6 is greater than 4, and hence we need to swap. The max heap property is violated, so we'll swap 6 and 4 and we will get this. But we are still not done yet, because we have been swapping and we have another parent of 6. So 6 will be compared with 9, and 6 is less than 9. Now here the heap property is satisfied, so we'll stop here. There is no need to swap, and we have placed 6 in its position. So finally we will have this array. Now notice where 6 has become the second most element, because it has become the second child of sorry, it has become first left child of 9, and 4 is here. 4 is the right child of 6. Now the next element is 11. I is pointing 6, and we will insert 11. So 11 will be inserted at the next available space, which means the left child of 7. So we insert 11 here, and then we do bubble up, which means we'll compare 11 with 7, and 11 is greater than 7. We need to swap because this violates the heap property. Once we are done swapping, 11 will be in the second level, and 7 will become its left child. But we are not done yet, because 11 needs to be compared with its parent again. And notice 11 is greater than 9, so which means we'll have to do another swap, and 11, which is the largest element, will now become the root of the tree. So we'll do a swap, and 11 has become the root of the tree, and 9 has become its right child. So this is what the reheaping or the bubble up property is. So it ensures that the heap property is satisfied, which means the left and right child of any node is smaller than itself. So once we have this, we are done, because there is no more parent of 11, and the array will look like this. Notice that 11 has become here, and the position of 9 and 7 have also changed during the bubble up process. Now next, I will increment, and I will become 7, which means the element 3 will be inserted as right child of 9, because that is the first position available. So 3 will be inserted here, and then we have to do a bubble up process again. So 3 will be compared with 9, but 3 is less than 9, so there is no need to swap, which means 3 has found its position, and we'll stop here. So 3 is done, so 3 will stay in its own position, and the array will look like this. Then I will increment, and I value is 8, which means it will point to element 5. Now 5 will be inserted at the first element in the 4th level, which means it will become the left child of 2. That is what the rule of insertion says. Now once we insert, we need to bubble it up till it acquires its position. So we will compare it first with 2. This will need a swap because 5 is greater than 2. So we will swap here, and here if you notice 5 and 2 are swapped. So let's see, 5 and 2 are swapped, but we are still not done. We have to compare 5 with its parent again to see if we will need more swaps. So we compare 5 with 6, but 5 is less than 6, which means heap property is still satisfied. There is no need to swap, and we are done here. There's no need to more comparison. 5 has found its position in the heap. So we are done, and then we will go to the last one where I is 9, which means element 10 needs to be inserted in the heap. So inserting of element 10, element 10 will become the right child of 5, because that is the first available position in the 4th level. So 10 is here. Now it actually violates the heap property, and we need to do a bubble up. So 10 will be first compared with 5. 10 is greater than 5. We need to swap. 10 will become the parent of 5, and 10 and 5 are swapped here, first step. So let's see, 10 and 5 are swapped, and then we are still not done yet. We have to compare 10 with its parent. We compare 10, and 10 is greater than 6. We need another swap. So 10 and 6 will be swapped. So now 10 will come to this second position, and 6 has been swapped. And notice we are still not done it. We have to do another comparison of the new 10 where it is with its parent. So 10 will be compared with 11, and 10 is less than 11, so this shouldn't be 5, this should be 11. So which means there is no need to do any more swap, and we have found the position of 10. And once we have found the position of 10, there is no need to swap, and we are done here. Now I will increment further, but notice I has reached the length of the array, so which means our bubble up process is now done. So this is the result of the bubble up or insertion procedure, which means we have finished inserting all the elements in the array. So bubble up process is complete. Now let's look back here again to our heap sort algorithm. So we are now done with 1 and 2. Yeah, it took a while, but since the bubble up process is complex, so we are just done with 2 steps. And now comes the next major part, which is to basically retrieve the element from the heap and then do a bubble down and then sort the elements. So let's now do that. So this is the element array, what it looks like after the bubble up procedure. So just at step 2. So after step 2, now in step 3 what will we have is we have j, which starts with length of a to 2, which means j is starts with 9. Now length of a is 9 because we have 9 elements, and in every step we will decrement j till we reach the second element. That is what it says, j less than 2. And what we do, we compare aj with a1, which means the first element is always swapped with aj, and then we do a bubble down a, or bubble down ai, bubble down a0, you can say, if you have seen the bubble down algorithm, because there were two bubble down algorithms we had. Let's say bubble down a1, which means bubble down the element at first position at the root to its position, and then once we are done, we'll decrement j again, which means the array size is now reduced and we have found one element, we have put one maximum element at its maximum position, and then we repeat this process. So let's now see this in action. So this was the heap which it looked like in the form of a tree, and the first step is to swap aj ai. So aj is 5 and 11, so 5 and 11 are swapped, you can see here. And once we do the swap, what we have done is we have placed the first item into its position, maximum element into its position. Why? Because the maximum, because this is a max heap and root is the maximum element of the heap. So once we have done, we are actually already sorted one element. Now we only have 9 elements which we need to sort. But then before that, since we replaced the item 5, now that has violated the heap property, and hence we need to do the bubble down process of 5 so that it acquires its position in the heap. So let's do the bubble down process. So here is the array. Now what the bubble down process does is it starts with root equals to 1, or it starts with bubble down a comma root in the other algorithm, but I mean this is okay here. So which means we have the root element which we need to bubble down. So now the bubble down process needs that we compare the element or the new root with its children to see which is the maximum of the children, and then compare and swap it. Now in this case, the child of element 5 is 10 and 9, and 10 is the maximum of the children. So we need to compare 5 with 10 and see if we need to swap. So we compare 5 with 10, and 5 is actually less than 10, so 10 should go up because 10 is the maximum element, and hence we will swap 10 with 5. And once we swap 10 with 5, so we get this array. And let's now see how the heap looks like. So 10 becomes the root and 5 is now here, but we are still not done yet because 5 has more children and we need to see if 5 has acquired its position. So what is the step? So first we will see its children. Its children are 6 and 4, and maximum of those is 6, and we have to compare 5 with 6, and 5 is less than 6, which means 6 has to be the parent of 5. So this violates the heap property, and hence we will swap 5 with 6. Once we swap 5 with 6, 5 goes here and 6 goes here, and it looks like this. So 6 now goes up and 5 now goes down, and then we are still not done yet because 5 has another child, so we have to now compare and see, compare 5 with its child and see if it is in its correct position. So we compare and we notice that 5 is greater than 2, and hence no more swaps required. We will stop here, and this means we have now placed 5 in its position. So after first round of bubble down, which means j equals to 9, we get this array as the output. So 5 has been bubbled down to its position here, and we have been able to sort one element at the end of the array. Alright, cool. Now let's go back. We'll return here and let's go back to the heap sort again. Now in the heap sort, what will happen is we'll go to step 6. J will be decremented to one step, which means j was 9. 9 minus 1 is 8. So we have j is now pointing to 2. And we will go to step 3 again, where we will actually see j if it is greater than 2, it is greater than 2, and hence what we do is we again swap aj with a1. Now in this case aj is 8th element, so 8th element is 2, so 2 will replace 10 and 10 will replace 2. So at the end of this operation 10 will go to the 8th position. So notice what has happened. We have now sorted 2 elements, which means we have picked 2 maximum elements and placed it at the end. But what we did is we replaced the root with 2, so due to which the heap property is violated, so we will have to call the bubble down algorithm and place 2 in its position. So let's do that then. So we have 2 now. So the first step, as we know, is we have to compare 2 with its children. Its children are 6 and 9 and find the maximum of it. The maximum of its children is 9, and we will compare 2 with 9. Notice 2 is less than 9 because 2 is smaller, 9 is greater, 9 has to go up. So we'll swap 2 and 9. Once we swap 2 and 9, we will get this. So 2 and 9 are now swapped, and we are still not done. 2 has 2 more children, which is 7 and 9, and maximum of those is 7. We'll have to compare 2 with 7, and notice we'll need another swap here because 7 is greater. So 7 will now become the parent of 2, and we will result in this. 7 and 2 are swapped here, and so 2 will become its left child. And once we do a swap, so 7, I think I have not shown it up here, but 7 will go here and 2 will go here. So this, and once we are there, 2 is now a leaf. 2 doesn't have any more children, so the bubble down procedure will stop here. So once we are done, we will end up having this as the array. And what will happen is bubble down process is done, then we will do a j decrement, which means j will now point to 7, and our tree will look like this. So 7 will go up, 2 will be the 7's left child. Now then we will go to step 3 again, and in step 3 j has to be decremented. J got decremented to 7. Then we will go to step 4, where we have to swap aj with a1, so which means this 3 will now be swapped with 9, and because 9 is the maximum element, 9 will now go to the end. So once we swap 3 with 9, we will end up in 3 elements which are sorted and at the end of the array. But now we have misplaced 3, because 3 will now violate the heap property, and hence we need to do a bubble down on 3 over here, bubble down, and that's what we will do next. So we'll replace 9 with 3. This is how 3 is at the root now, and we have to do a bubble down. To do a bubble down, we have to compare and see what its children look like. Its children are 6 and 7, and the maximum of its children is 7. So we need to compare with 7 and see if we have to swap it. We compare 3 with 7. 3 is less than 7, so this needs to be swapped because 7 is greater. 7 has to be the highest or the root. So 7 will be now swapped with 3. Once 7 is swapped with 3, so 3 and 7 will be swapped. 7 will get the root position, the maximum position, and 3 will have its new children, which is 2 here. Now in this case there is only one child, so we have to still compare it with 2 and see if there is further bubble down is required, or if 3 is in its position. So only child is 2. We compare 3 with 2. 3 is greater than 2. Heap property is intact. There is no need to swap, and hence we are done. So there is no need to do any more swaps, and the bubble down process is ended. So at the end of bubble down, this is how the array looks like. Now we will go back again in the heap sort algorithm, and j will get decremented. J will get decremented again to 6, and the first step is to swap the maximum element or the root element with this element, and then this is what it will look like. So 7 will replace 2, and notice what has happened. We have got 4 maximum elements that are sorted at the end, but then 2 has been misplaced and 2 has to be bubbled down till it's find its position. So we'll call bubble down A1, which means bubble down 2. Now you can actually ignore the 1 here because we are anyway doing bubble down from root here, so we are just doing bubble down root. So what will happen is we have 2 here, and then we need to bubble down 2. So 2 has to be compared with its children. Its children is 6 and 9, and 6 is the maximum, so we have to compare with 6. 2 is less than 6, which means 6 now needs to be swapped up. We swap it. Once we swap it, 2 becomes at the place of 6, but we are not done yet. We have to compare 2 again with its children. Its children are 5 and 4. 5 is the maximum, and we need to compare with 5. 2 is less than 5, and hence 5 needs to be swapped up, and 2 will become its child. So we swap, and then finally we will have 2 here and 5 here, so both of them are swapped. So let's see how it will look like. And once we have swapped them, there is no further swap needed, so this will become 5 here, this will become 2 here. So 2 has found the lowest position, there are no more children, so our bubble down process will end here. The next step is again j would have decremented by 1 more value, which is 5, and we will have the maximum element as 6, which is the root. So the first step is to swap the maximum element with aj, so 6 and 4 are swapped. So 6 will come to the end of the sorted array, and now we will have 5 elements as sorted. But then 4 is now misplaced. 4 is the root, we have to bubble down 4. So bubble down 4, 4 will be compared with its children. Its children is 5 and 3. 5 is the maximum. We compare 4 with 5. This is not we'll have to compare 4 with 5, and because 5 is greater, 5 will move up and 4 will move down. So we'll have to swap, and 5 and 4 are swapped now. And then what will happen is 4 has to be compared again with its child. In this case there is only one child, which is 2. We'll compare 4 with 2, but 4 is greater than 2, which means the heap property is not violated. We are good, so our bubble down process stops here. There is no need to swap further, and then we will just return, and in this case 4 has found its position, which is the second place. We'll return. Once we return, j value will decrement again. J was 5, now j becomes 4. J is now pointing to 2. First step is to swap j with the first element, which is 5, is the maximum element 5. We swap, and once we swap, we will have 5 at the end of the remaining array, and then we will now have 6 elements that are sorted, and our heap is only reduced to 3 elements, and 2 is now in its misplaced position, so we have to fix 2. So we'll call bubble down a. 2 is now the root. 2 has to be compared with its children. Its children are 4 and 3. 4 is the maximum. We'll compare 2 with 4, and 4 is greater than 2. 4 has to move up, 2 has to move down, and hence we swap, and 4 goes up, 2 down, 3, and we end here because 2 now has no more children. So our bubble down process ends here, and we are left with this array, which is over here. Now notice how the number of elements are reducing in the heap, and the number of elements that we have sorted are increasing. So now the next step is j will now be pointing to 3, and we need to swap aj with a1, which is 4. So 4 and 3 will be swapped. Once 4 and 3 is swapped, 4 is also sorted. So we have now 7 elements sorted, and 3 will replace 2, so we need to fix the position of 3. We need to bubble down 3 to its position. So bubble down a1, we only have 2 elements, 3 and 2. So 3 has only child 2. 3 will be compared with 2, and there will be no swap because 3 is already greater than 2. So then we will be done with bubble down because there is no more comparisons needed, and the final array will look like this. Cool. So next j we return here, and next j will become 2. Now notice this is the last iteration for j because j started from 9 to 2, if you remember the loop which we had. So in this case 2, we have to replace second element with the first element, so 2 and 3 are swapped, and 3 is now swapped and placed into its position, and we now have 8 elements which are sorted. Once it's done, we will have to fix 2, because there is single element, there is no need to fix it, by itself is fixed, or there is no need to bubble down, or even if we call bubble down, there is nothing that will happen, because there are no more children of 2, and we are now done. So finally what will happen is the bubble down loop, the for bubble down loop will end here, because j will now be equal to 2, and once we are done with the sorting procedure. And notice what will happen, the last element by itself is sorted, and hence finally we have sorted all the 9 elements. So this is the final sorted array. Alright, cool. So I hope this detailed example helped a lot to understand how the heap sort works. I hope it wasn't that lengthy, and if there was any confusion, you can always go back to the video and see the steps in detail. Alright, so the next step is to do a time complexity analysis of heap sort like we did for the other algorithms. So heap sort analysis, if you remember the bubble up and bubble down procedure in the other video which we have in heap, in introduction to the heap video, binary heap video, we have already computed the complexity of bubble up and bubble down, because these are important procedures that form the heap sort. Now in bubble up procedure, what happens is, if you notice, there is one while loop which actually starts from the parent, and it actually runs till parent is greater than 0, which means when we add an element to the heap, we add the element at the end of the heap, so at the last element n, and every time we compare it with its parent, so parent is nothing but a index by 2, till the element finds in its space in the existing array. Now because in this case it's not a linear decrement, it's actually in a logarithmic decrement. The number of steps the bubble up takes is actually log index, so which we can say is log n. So which means if there are n elements in the array and we are inserting one element, it will need log n comparisons to actually place the new element to its position. So that's why the bubble up complexity is log n. Why? Because we first assign parent because we first assign the element at the end, which is n, at the position n, and then we find the parent, and then what we do is we go back one step. So if this was a heap, we'll insert the element here, and then we go back in the tree like this till we get the parent is greater than 0, so which is nothing but log n steps. Similarly, the bubble down process, what happens is, in this case we start from the root and then we go down one step at a time by first finding the left child and then the root left child and then the right child, and then we compare, and then we bubble down the element that we had replaced in the root. So this is also log n comparisons, which means it's actually exactly log n, because we start from the root and then we have left child and right child, and we reassign left child and right child till we reach the leaf. Now it's possible that we find that the element is already smaller, which means the child is already smaller than the root, which is our best case where we will have to stop, but in the worst case or in the average case we will need our log n number of comparisons to actually bubble down the element at root to its position. So that's why even bubble down needs log n. So now let's go back and look at the heap sort algorithm. Now in the heap sort algorithm we had two loops. Now there is a for loop here first, and then there's a for loop down. Now the first for loop runs from 2 to length a, which is n minus 1 times, and every time we call the bubble up inside it. Similarly, the second for loop starts from j equals to a to 2, and this also runs n minus 1 times, and in every call we call the bubble down. Now we know bubble up and bubble down actually take order log n. So let's now compute the complexity of heap sort. Now complexity of heap sort is nothing but n minus 1 times the bubble up, because bubble up is called n minus 1 times and bubble up is log n. Similarly, n plus n minus 1 times bubble down. Now bubble down is also log n. So if we actually solve this equation and we ignore the lower numbers in the polynomial and we use a complexity analysis, we will see that the complexity is nothing but order n log n. And notice this is actually for all the type of input data, so which means for best case, average case and worst case, in all cases we need to still do bubble down and bubbled up, and actually heap sort performance is independent of the distribution of data. It's similar to what merge sort was, so it doesn't matter if the data is sorted or unsorted, we will still need to do bubble up and bubble down even in average case, best case and worst case, and hence this is all the three cases we have order n log n. And if you have noticed, merge sort was also order n log n, and hence these two are one of the best sorting algorithms that we have. And also it doesn't matter if the data that they are sorting are sorted or unsorted, in all cases they will take order n log n, which is actually good. Alright, cool. So that was the complexity analysis. And actually we are now reaching the end of the video. I hope it wasn't that long. So before we end, here is an exercise. In fact, we have an array. We're given an array with 10 elements, and then we request the viewer or the reader to sort the array using the heap sort, which means using the bubble up, bubble down procedures. And then while doing that, make sure you do compare the total number of comparisons, count the total number of comparisons that you need during the sorting process, during both bubble up and bubble down. So once you do that, you will get an idea of how many comparisons were needed. And if you have been doing that with the other videos, like the insertion sort and selection sort, so you might see compare these number of comparisons, and you might see a good difference to see which algorithm or which sorting algorithm is better. Alright, cool. So that was all I had in this video. If you guys like our videos, make sure to subscribe to our channel. If you had any comments or you want me to cover any areas in greater detail, please do comment on the video, and I'll see what best I can do. Thank you guys.